Welcome to lecture 12 on measure and integration. If you recall, last time we looked at the extension of a measure from an algebra to the sigma algebra generated by it and slightly beyond the class of all outer measurable subsets. Today, we are going to look at some special applications of this, a particular case of that extension theory for the real line, and that is the topic for today's discussion, namely Lebesgue measure and its properties. So, for the extension theory, we are going to apply it for the case x is equal to real line. The set is the real line. The algebra A, which is the algebra generated by all intervals in the real line, and mu on this algebra is the length function that we had defined, and we had seen that the length function on the algebra generated by all intervals is a countably additive set function. The outer measure induced by this length function, which is denoted by lambda star, is on all subsets of the real line, and that is called the Lebesgue outer measure. So, the outer measure induced by the length function is called the Lebesgue outer measure. Let us just look at what is the Lebesgue outer measure for a subset of the real line. So, if you recall, we defined it as outer measure of a set E is look at all possible coverings of the set E by elements in the algebra. But here the algebra being the algebra generated by intervals, it is finite disjoint union of intervals. So, we can write this outer Lebesgue measure as the infimum over summation lambda of the intervals I I, where the intervals I I's form a covering of the set E, and these intervals are pairwise disjoint. So, lambda star of E is the infimum of the sums of the lengths of the intervals which form a covering of E, and then we can take these intervals to be disjoint, because if not, then we can make them a disjoint. So, that is the Lebesgue outer measure for a set E. The class of all Lebesgue outer measurable sets, so lambda star measurable sets, is called the sigma algebra of Lebesgue measurable sets. So, the sets which are outer measurable with respect to lambda star is called the sigma algebra of outer measurable or Lebesgue measurable sets, and is denoted by L suffix r. Just to indicate L for the Lebesgue and R for the real line. In case there is no confusion, we will just denote L R by simply L. So, it is a class of all Lebesgue measurable sets. If you recall, we had also defined the sigma algebra of Borel subsets of real line, and that was the sigma algebra generated by all intervals, and A being the algebra generated by intervals. So, the sigma algebra generated by finite disjoint union of intervals is same as the sigma algebra generated by all intervals, and that is same as the definition of the Borel sigma algebra of the real line. So, these properties we had already seen. So, the length function in particular is also defined for all Borel subsets, because the sigma algebra generated by A is inside the class of all outer measurable sets, that is L. So, we have got that S of A, that is the Borel sigma algebra, is inside the class of all Lebesgue measurable sets. So, for all Borel subsets, the notion of length is defined. So, this is called the Lebesgue measure. So, let us just summarize what we were saying. We are saying that the extension theory, when applied to the particular case of the real line, gives us the notion of length for a class of subsets of the real line, which are nothing but the class of outer Lebesgue measurable sets, and that includes the class of all Borel subsets. So, that is also that gives us the notion of length for all Borel subsets of the real line. So, the triple R Lebesgue measurable sets, the length function as extended by the extension theory. This triple is called the Lebesgue measure space. So, the extension theory applied to the real line gives us the notion of the Lebesgue measure space, and it extends the notion of length from intervals to the class L of all outer Lebesgue measurable sets. Let us just recall that the sets Borel subsets form a subset of the class of all Borel sets is a subclass of the class of all Lebesgue measurable sets, and of course, Lebesgue measurable sets is a subclass of all subsets of real line. So, the question is, can we say something more regarding these three classes, namely Borel subsets, Lebesgue measurable sets and PR. So, let us observe which we have done during outer measures, that the Lebesgue measurable sets are characterized by the Borel subsets of the real line union the null sets. So, what are the null sets? Sets in the R, subsets of R such that n is contained in a Borel set of measure 0, or equivalently one can also define it as sets of outer Lebesgue measure 0. So, B R is a subset of L. We know that outer measure 0 sets are also measurable. So, this and we said this class is nothing but this forms the sigma algebra, and that is equal to the Lebesgue measurable sets. So, that means the B R union n is equal to L. So, all null sets are part of L, but we want to characterize what is the relation between B R and L and what is the relation between L and P R. So, at present we only know that the Borel sets are subsets of all Lebesgue measurable sets, which is a subset of P R. To say something more, we need to look at what is called a special subset of the real line called Cantor's ternary set. So, we are going to spend some time on a special subset of real line, which is called Cantor's ternary set. And Cantor's ternary set is an example of a set which has very nice properties, and it is useful both from the topological point of view as well as measure theoretic point of view. So, let us look at what is called Cantor's ternary set. Ternary. It is called Cantor's ternary set because it was given by the mathematician George Cantor, first defined by George Cantor, and ternary set because it involves ternary expansions of real numbers. So, what we are going to do is, it is a construction, we are going to construct a Cantor's ternary set. So, as a step 1, let us look at the interval 0 to 1. So, I will first describe this process of Cantor ternary set construction, and then we will analyze its properties. So, what is the first step? The step is divide this into 3 equal parts. So, that is 1 by 3 and 2 by 3, and remove the middle open portion. So, this open portion is removed from the interval 0 1. So, what it gives? It gives us 2 pieces 0 to 1 by 3 and from 2 by 3 to 1. So, it gives us 2 closed intervals. So, at the first step, at the first stage, having removed the middle 1/3 of the closed interval 0 1, middle 1/3 open interval, we get these 2. And now, we repeat that process again with these 2 sub intervals. So, from each of these sub intervals, remove the middle 1/3 portion. So, that is middle 1/3 is 1 by 9, 2 by 9, and here the middle 1/3 will be equal to 7 by 9 and 8 by 9. So, this is the middle 1/3 portion, which we are going to remove at the second stage. So, that will give us 4 sub intervals, and we continue this process. So, eventually something will be left. So, continue. So, the question is what is left? What is left is called Cantor's ternary set. So, let us analyze and let us denote this set Cantor's ternary set by the letter C. So, how do we mathematically construct this? So, that is the question. So, for that let us start with the first stage, that is A 0, that is the closed interval 0 1. After having performed the first stage, what is left? I write it as A 1. So, that consists of two disjoint intervals 0 to 1 by 3 and 2 by 3 to 1. So, it consists of two disjoint intervals. So, let us write them as at the first stage 1 union the second one, first stage the second one. Okay. So, this portion is the first interval and this portion is the second interval. That is I 1 1 and this one is I 1 2. So, at the second stage we will be left with 4 disjoint closed intervals. So, let us write them as union I second stage j equal to 1 to 4. So, that is going to be 2 raised to power 2. And let us see what will be at the nth stage. If we continue this process at the nth stage, how many intervals will be here? So, there will be intervals, how many of them? We start with 1, at the next stage 2, at the next stage 4 and so on. So, there will be disjoint intervals j equal to 1 to 2 to the power n, there will be 2 to the power n closed sub intervals of 0 1. Let us write them as I n j. So, these are the intervals. So, what is A n? A n is the union of those intervals which are left at the stage at the nth stage. And what we want? And we continue this process, we want what is C. So, how do we write mathematically C? So, the Cantor set we can write it as, so the Cantor set C we can define it as intersection of A n's n equal to 1 to infinity, right. So, each A n is a subset of the previous one, right. So, let us write what is left eventually as intersection of all these A n's. So, this is what is called Cantor's ternary set. So, let us make some observations about this. So, observations about this Cantor's ternary set. The first observation is that the endpoints of the open intervals removed are in C. Say for example, 0 is, so 0 is not removed, is not going to be removed, 1 is not going to be removed. At the first stage we removed the open middle 1/3. So, 1 by 3 is not going to be removed, 2 by 3 is not going to be removed, and at the next stage 1 by 9 will not be removed, 2 by 9 will not be removed, and similarly 1 by 3 we have already listed, then 7 by 9 will not be removed, 8 by 9 will not be removed, and so on will not be. So, for example, these points will not be removed, they will stay in this process of removing middle 1/3 open interval from each subinterval at every stage. So, that means, so thus the class C, the set C is a non-empty set, it is non-empty, is non-empty. So, that is the first observation, there is something left behind. Okay. And the second observation we want to show that in fact C is uncountable, that it is an uncountable set. So, how do we prove C is uncountable? What we are going to do is, we are going to define a map from the closed interval 0 1 to C. So, to prove this, we will define a map which is 1 1. We will define a 1 1 map from 0 1 to the Cantor's ternary set, and that will prove that the cardinality of the set C is at least as much as 0 1, and C being a subset of 0 1, it cannot be more than that of 0 1. So, cardinality of C will be same as cardinality of 0 1. That may seem a very strange observation to you, that from C we have removed, from the interval 0 1, we have removed so many pieces, and still what is left is as much as the points in 0 1. So, these are properties of infinite sets. Actually, they are the characterizing properties of infinite set. The interval 0 1 is an uncountable set, and from that we are removing sub intervals, and still what is left behind is as much as 0 1. So, let us prove this fact, namely that there is a 1 to 1 map for this. So, for this let us start, let us take a point x belonging to 0 1 and consider its binary expansion. So, what is the binary expansion? The binary expansion of a point in 0 1 is written as, so x can be written as point a 1, a 2, a 3, a n and so on, where each a n is equal to 0 or 1. So, that is the binary expansion of every point. Essentially, the idea is that the interval 0 1 can be divided into two parts, name first part as 0, second part as 1, and see at each stage where it lies. So, that is 0 and 1. And let us assume, see, there are two different ways of writing, for some points there are two different ways of writing binary expansions. So, we will fix one of the ways and say there is a unique binary expansion for every point in 0 1. So, we will fix that binary expansion process. Okay. And now, what we do is the following: construct a point y with ternary expansion b, with ternary expansion. So, y is equal to point b 1, b 2 and b n, where for every n, b n is nothing but 2 times a n. So, even the binary expansion, look at the nth place, either it will be 0 or 1, double it and call that as b n. So, b n is twice as much as a n. So, each b I is either going to be 0 or it is going to be 2. So, this is the ternary expansion. So, note y belongs to 0 1, because it is dash, is dot b 1, b 2, b 3 so on. So, no integral part. So, it is going to be part of, it is a point in 0 1, and it has in the ternary expansion the only numbers that come are 0, 2 times a n is 0 or 1, it is 0 or 2. So, in the ternary expansion of y which is in 0 1, only 0 or 2 appear, and that implies that y belongs to C, because in the construction of the Cantor ternary set we have removed the middle 1/3. So, in the ternary expansion the number 1 is not going to appear. So, each one is, so this is a part of. So, this is the observation we make, that starting with a point x belonging to 0 1 with binary expansion a 1 a 2 a n, construct a point y. So, send it to the point y. So, this x is sent to the point y, which is again in 0 1. In fact, it belongs to So, let us write more specifically it belongs to C. So, we have got a map from 0 1 to C, and the claim is that this map it is 1 1, and that is obvious because for every point x we have got this binary expansion a 1, a 2, a 3, a n, the unique binary expansion. So, if you take two different points x 1 and x 2, so let us try to write this mathematically, that this is. So, let us take a point x 1 with binary expansion a 1 1, a 1 2, a 1 n, and so on, and let us take another point with unique binary expansion that we have fixed the methodology. So, a 2 1, a 2 2, and a 2 n, and so on, and x 1 not equal to x 2. So, that implies if x 1 is not equal to x 2, that implies there exists some stage n naught such that a 1 n naught will not be equal to a 2 n naught, and that implies that 2 times a 1 n naught will not be equal to 2 times a 2 n naught, and that is this is b 1 n naught, and this is called that b 2 n naught. So, that means y 1, if we have y 1, that is point b 1 1, b 1 2 up to b n n, and so on, and y 2 is the other point, the image of x 2. So, that is b 2 1, b 2 2, b 2 n, and so on. Then, so if this is so, then y 1 is not equal to y 2. So, that means this process of sending x, taking x with binary expansion as this, and constructing y with ternary expansion as this. So, if we send x to y, this gives us a map from 0 1 to C, which is 1 1, and hence, so this implies as a consequence. So, hence the cardinality of C is same as cardinality of 0 1. And if you recall, cardinality of 0 1, that is, so let us write this implies that C is uncountable, because 0 1 is uncountable. So, thus C is an uncountable set. So, this is follows from our construction that C is an uncountable set. In fact, let us try to now calculate. So, note that C, which is equal to intersection of a n's, implies that for every n, C is a subset of a n. And what was a n? That was a disjoint union of intervals I n j, j equal to 1 to 2 to the power n, right. And at the nth stage, what will be the length of each where? The length of each I n j. So, what is the length of the intervals which are left at the nth stage? That is 1 over. So, let us just look at the construction. At the first stage, when we removed at a 1, 2 intervals were left, each of length 1 by 3. So, this is 1 by 3, this is 1 by 3, this is 1 by 3, and this is 1 by 3. So, 4 intervals at the second stage of length 1 by 3. So, at the nth stage, how many 2 n intervals of each of length, how many will be left? There are 2 to the power n intervals, each of length how much? So, here the length of each I n j. So, at the second stage it is 1 by 3, second stage is 1 by 3, and so nth stage will be 1 over. So, it will be 1 over 3 raised to power 2 n minus 1, right. So, that will be the length of each one of them, and there are 2 to the power n of them. Okay. So, what is the total length? So, sigma lambda of I n j, j equal to 1 to 2 to the power n. So, that is 2 to the power n intervals, each has got the same length. So, divided by 3 raised to power 2 raised to power n minus 1, and observe that this number goes to 0, right. It is 2 to the power n by 1 over 3 raised to power n, that goes to 0 as n goes to infinity. So, that means what? That means that C can be covered by, for every n, by 2 to the power n intervals whose length is this, and that can be made as small as I want. So, that means that the outer Lebesgue measure, so lambda star of C is equal to 0, right, because what is lambda star of E? It is the infimum of the sums of the intervals which cover the set C, and we are here we have just now shown that C is contained in A n, which is a finite disjoint union of intervals, and the total length of these intervals is becoming smaller and smaller. Okay. So, that is length of C. So, that implies that C is a lambda star null set. Hence, C belongs to, is a Lebesgue measurable set. And not only that, C is Lebesgue. In fact, what we know is something more, that if E is any subset of C, then that implies that lambda star of E also equal to 0, because lambda star is monotone, and that implies that E also belongs to L. So, thus hence all subsets of C, power set of C is a subclass of the Lebesgue measurable sets, and of course, Lebesgue measurable sets are a subset of power set of real line. Now, but C is uncountable and R is uncountable. So, what does this imply? That means, this implies that L has as many elements as P of R. So, what is the meaning of this, has as many elements as P R? That is same as saying the cardinality. If you know what is cardinality, cardinality of L is same as the cardinality of the power subset of real line. And if you know that the cardinality of real line, which is the what we call as cardinality of continuum, is denoted by the small letter c. So, and this is denoted by 2 to the power c. So, there if you look at, so that what does that prove? So, that proves that if you look at from the cardinality point of view, if you look at how many elements are there in the class of all Lebesgue measurable set, then it says cardinality of Lebesgue measurable sets is as much as the cardinality of all subsets. So, if you look from the cardinality point of view, you cannot say that the class of all Lebesgue measurable sets is a proper subset of the class of all subsets of the real line. So, but that does not also imply that all subsets of real line are Lebesgue measurable. So, the question still remains undecided whether the class of all Lebesgue measurable sets is a proper subclass of all all subsets of real line. So, to decide this, the question is a bit difficult, and that relates to some fundamental questions in set theory. So, let us look at so what we have shown just now. Let us just recapitulate that lambda star of C is equal to 0, and that says that power set of C is a subset of L, and hence there are at least as many elements in L as 2 to the power C. So, that is the cardinality of the continuum. So, we get cardinality of L and power set is same, both have got same cardinality. So, question still remains, is L a proper subset of PR. So, if you recall, the answer to this question is related to some of the fundamental questions in set theory. So, if you recall, we proved what is called Ulam's theorem. We did not prove it really. We mentioned what is called Ulam's theorem, and I said that one can read a proof of this in the textbook that we have mentioned, and that statement of the Ulam's theorem says, assuming continuum hypothesis, Lebesgue measure cannot be extended to all subsets all of real line. There is something called continuum hypothesis in set theory. I will not explain at this stage what is continuum hypothesis, because we will be going slightly off stream, but it is worth mentioning here that the set theory is based on certain axioms. So, whatever modern mathematics we are doing is based on axiomatic set theory, and there is a which has some kind of some axioms on which we can deal with set theory, but there is something called continuum hypothesis which relates to the subsets of real line and so on, and that is not part of the axioms of set theory. That is why it is called continuum hypothesis. Some people believe in continuum hypothesis and do mathematics according to that, and some people do not believe in it. So, if you assume continuum hypothesis, then Ulam's theorem says that you cannot extend, that means not all subsets of real line are measurable. Another result which one can use, which is again not part of the axiomatic set theory, is the following, which says that supposing you assume what is called axiom of choice. Axiom of choice is another axiom which is not part of the axiomatic set theory, and one can either accept it part of set theory and do mathematics, or do not accept part of it and do mathematics. So, mathematicians, those who accept axiom of choice, they are supposed to be doing what is called non-constructive mathematics, because there are some existence theorems which assume axiom of choice helps in proving some theorems which are existential in nature. For example, proving that every vector space has a basis, it requires the need of using axiom of choice. You cannot prove it if you do not assume axiom of choice. There are many results in mathematics which use axiom of choice and which are not true if you do not assume axiom of choice.